Good morning, everyone. Welcome to VSPG. Today we have a presentation by Dr. Volker Schenk from Heidelberg University. His talk is titled Evidence for One-Sided Oceanic Subduction in the Palaeoproterozoic Paired Metamorphic Belts in the Usagaran orogen of Tanzania. Next week, we have a speaker by Dr. Nora Nafki at Old Dominion University. That talk is titled A Fossil Microbial Ecosystem in the 3.48 billion Dresser Formation in Pilbara, Western Australia. So join for that next week. I don't have any announcements today, so I'm going to switch it over to Andre for any announcements and to introduce Volker for us.
Yeah, great. So we have only one announcement. So for June 2nd, Don Sumner won't be able to present for family reason. And we got on a short notice Christoph Hubik, who will present on drilling project in Barberton Greenstone Belt. And after that, we have a full schedule until mid of June, break until late September, and then full schedule until New Year. So with this, it's a pleasure to introduce Volker Schenk from University of Heidelberg. We met with Volker on a field trip in Brazil probably 10, 15 years ago. And as we got into talks about plate tectonics, and when it started, I thought it would be great to have introduction from Volker about eclogites and subduction zones. So Volker got his undergraduate degree and I guess master in University of Marburg and Göttingen in Germany, and he worked on chalidonites in northern Sweden. He followed with PhD in 1978 in Ruhr University of Bochum, again in Germany, focused on metamorphic petrology and working in Western Mediterranean Alps. He followed with postdoc at the University of Münster and Max Planck Institute of Mainz, working in the same area, but using geochronology. He studied as a professor of petrology at the University of Kiel in 1985 and did a number of projects on metamorphic evolution of orogenic belt in Africa and India with ages from Neo-Proterozoic to Palaeoproterozoic and Neo-Archean. And later in his career, he became interested in subduction zone metamorphism, Precambrian eclogites, and fluid interaction process and paleo-subduction channels. And he is one of the world famous experts on eclogites and especially on oldest eclogites. So with this, it's a pleasure to pass to Volker. And Volker, please unmute yourself.
Yes, go ahead and unmute yourself and share your screen. All right, looks good. But we can't hear you yet, Volker. Sorry, we can't hear you yet. So
now it works.
No, yeah, we can hear you now. Perfect.
Okay. Andre, thank you very much for your introduction. But I want also to thank the organizers for this interesting and enjoyable seminar that they invited me to present my work on Precambrian eclogites, which are found in several Precambrian orogenic belts in Africa. And before I start, I want to point out that the results I'm presenting rely to a great part on the contribution of my co-authors, which is Daniel Wiemer, Topo Saka, and Axel Schmidt, also here from Heidelberg. As the title of my talk is saying, I will try to present pathological evidence that paired metamorphic belts, in the original sense of Miyashiro, developed in several Palaeoproterozoic orogens, and that this is evidence for one-sided oceanic subduction operating already in the Palaeoproterozoic. As some authors, have described paired metamorphism or paired metamorphic belts in Proterozoic or even Archean origins, which, to my opinion, have not the characteristics and the lithological inventory of paired belts in the sense of Miyashiro. I want to clarify that I will describe paired metamorphic belts that are spatially and timely associated and consist or contain at least in its high pressure part subducted oceanic crust in blue-schist or in eclogite phases. This is as it was described originally 60 to 50 years ago for the Circum-Pacific origins by Miyashiro. These are the original graphics published by Miyashiro in the 60s and 70s. In the last 20 years or so, many authors are searching for indicators for the beginning of plate tectonics on Earth. Some of these authors have shown that the rock record of metamorphic belts, the evidence that cold subduction may have started only in the Neoproterozoic. I think several months ago in the seminar, Mike Brown showed this diagram. Data displayed in this diagram clearly indicate that there are only few metamorphic rocks known that fall in the thermal regime of cold subduction and are older than 800 million years, whereas many PT data for metamorphic rocks younger than 800 million years fall into the cold subduction regime as defined by Brown and Johnson 2018. When this cold subduction regime started to exist is better displayed in this graphic in the upper part, as it shows apparent geothermal gradients of metamorphic rocks plotted over the geological time. It is obvious that subducted rocks that are older than 800 million years are nearly absent. Authors who have considered not only the thermal conditions of metamorphic rocks, but also the rock type, which are typical for subduction or collision, came to a similar conclusion. The shown diagram is from Stern, but further authors have also developed this diagram. Rocks like blue schists and lawsonite-bearing rocks or ultra-high pressure rocks are nearly absent in the rocks of pre-Neoproterozoic time. These recently published diagrams illustrate that some indications exist that subduction of cold oceanic crust may have started only in the Neoproterozoic. Paired metamorphic belts, in the sense of Miyashiro, paired in space and time, are not displayed in these diagrams, but are so far only known from the Phanerozoic. However, a duality of thermal regimes, one with low TP ratios, another with high TP ratios, existed in the known metamorphic datasets and were used by the authors to deduce that modern type of plate tectonics existed at least within the Palaeoproterozoic. Their interpretation implies that the duality of the regime, thermal regimes, is produced only by subduction processes, whereas other tectonic processes are not considered as possible causes of this duality. I have to point out that the duality of thermal regimes is distinct from those of paired metamorphic belts in the sense of Miyashiro, as the considered belts in this plot are not belts that are spatially and timely associated, and there is no proof that in these low TP belts contain subducted oceanic crust. On the right side of this diagram, it's shown that the duality of thermal regimes started somewhere here in the Palaeoproterozoic, but became more pronounced in later geological times. And it is the aim of my talk to demonstrate that paired metamorphic belts in the sense of Miyashiro already existed in the Palaeoproterozoic origins and thus present evidence that paired metamorphic belts in the one-sided oceanic subduction occurred already in the Palaeoproterozoic. The following part of my talk will cover the topics listed here. I will start with the metamorphic evidence for subduction of oceanic lithosphere, cold subduction of oceanic lithosphere prior to the Neoproterozoic. Then I will explain the geology of the Usagaran orogenic system in Tanzania. Then in the main part, I will present the chemistry of the eclogites and the metamorphic history of eclogites and the associated metasediments in a high pressure belt, in a low pressure belt. And from these data, I will deduce a geodynamic model for the development of the paired belts in the Usagaran orogen. And finally, I will discuss and present the common characteristics of the known Palaeoproterozoic paired metamorphic belts. I start with the metamorphic evidence that exists for cold subduction prior to the Neoproterozoic. For this purpose, I'm showing the map of the Columbia-Luna supercontinent, where the Palaeoproterozoic orogenic belts are shown in blue. And I have added to these belts the places where ultra-high pressure and eclogites have been described. These are about 10 orogenic belts. But most of these belts contain eclogites that formed from dikes in thickened continental crust, and only few existed that are produced from subducted oceanic crust. And these occur only here around the Congo Craton in Palaeoproterozoic orogenic belts. We can show these Cambrian data for eclogites in this diagram stern, which I have modified by adding the information that we have from the Cambrian eclogites. And I have divided these eclogites into the group that have morph chemistry and those that are formed from dikes and thickened continental crust. For those which are subduction related, occur in the Palaeoproterozoic and in the Neoproterozoic, whereas in thickened continental crust, we have also some in the Mesoproterozoic time. I will talk about the Usagaran and the Ubendian belt, which are presented here by these two stars. Coming to the geology of the Usagaran orogen along the Tanzania Craton. This map of Eastern Africa shows the position of the Tanzania Craton, the Bangiulu block, Zimbabwe Craton, and at the southern side of the Tanzania Craton, we see in brownish colors, the Palaeoproterozoic orogenic belts, the Ubendian on the southwestern side and the Usagaran on the southeastern side. Both belts contain subduction-related eclogites, here in the northern end in the Usagaran, and here also in the northern end in the Ubenya. The horizontal hatching that is shown here, that covers the brownish colors of the Palaeoproterozoic belt, is due to the fact that the Palaeoproterozoic belts are in great parts reworked to Neoproterozoic tectonics, the Kounga reworking Neoproterozoic time. And this is thought to be caused by net transport of Neoproterozoic granulites towards the Tanzania craton and the Usagaran belt. This is a map of the Usagaran made by Fritz, and this is based on maps that are published by the Geological Survey of Tanzania and the German Geological Mission. However, the boundaries shown in this map are not correct. The regional extent of the Usagaran is much wider. And we found this out when we were studying the meta sediments for the metamorphic history in these points shown in red. And by texturally controlled monocyte dating. What does it mean, textural controlled monocyte dating? When we dated monocyte that was included in garnet, then we obtained ages that were always Palaeoproterozoic in age. When we dated monocyte in the matrix, we obtained only Neoproterozoic ages. And we can see on this map that far outside the boundaries of the known Usagaran orogenic belt, we find everywhere metamorphic ages outside of Palaeoproterozoic age. And the main metamorphism was obviously the Palaeoproterozoic one, because the garnet growth was the higher grade of metamorphism. And this occurred far outside the known boundaries of the Usagaran orogenic belt. The picture is more obvious when we also regard the magmatic formation ages in this part of the belt. And we see here the Palaeoproterozoic in brownish colors and the Archean ages in red colors. And this indicates clearly that to the east of the boundary of the Usagaran belt, we have also Palaeoproterozoic granulites. So in fact, large parts of the so-called western granulite, which are regarded to be Neoproterozoic in age, are in fact Usagaran overprinted by the Kounga event. Let us have a closer look at the geology in the area where the paired metamorphic belts have been developed. This is restricted to a smaller area. This map is mainly based on the mapping by Meinhold in the 60s, and it shows that the Tanzania craton is overlain mainly by three different, mainly sedimentary groups. The Conzo group, the lower Isimani group, and the upper Isimani group. So the Conzo group resting directly on top of the Tanzania craton and is interpreted as either a passive margin sequence or a post-orogenic sediments deposited after the Usagaran orogeny. The lower Isimani group I would like to interpret as an accretional wedge sequence, and it includes these greenish rocks shown in green. The eclogites are therefore the high pressure and low temperature belt. And the upper Isimani series hosts the low pressure, high temperature belt. And these are mainly sediments that have been accreted to an arc and experience there the high temperature metamorphism. And the last member are Mozambique belt metacraton, which is hidden in the Neoproterozoic Mozambique belt further in the east. If we had a look at the phase relations of the metapelites in the lower Isimani series and the upper Isimani group, then we see they are very distinct contrasting. The lower Isimani group has kyanite and garnet, whereas the upper Isimani group has silimalite, cordierite garnet. So this is a first indication that there might be a paired metamorphic belt because they have been formed in totally different geodynamic settings. The Conza group, which is interpreted in different ways, is a sedimentary sequence that follows the Tanzania craton for about 200 kilometers. Meinhold estimated the thickness of the sedimentary sequence to 500 to 1,000 meters and described an increasing metamorphism from west to east, from green schist to lower amphibolite facies. The sequence consists in the basic quartzite conglomerates, which are overlain by mica schists. Contains also dolomitic marble and the characteristic manganese silicate mica schists. The sequence has been interpreted in two different ways: post-orogenic, in intracontinental basin succession, and should deposited discordantly on the folded Usagaran basement. And this interpretation is because these authors regard these sediments as a time equivalent of the Canberra volcanics that have been dated here in the south. And the other interpretation is from Meinhold, and he interpreted as a time equivalent of the lower Isimani series, just deposited nearer to the craton. To solve the problem, we dated the metamorphic monocyte in the Conza group, the lower amphibolite facies, and we obtained an age of 2027 million years. And this age is the age of the Usagaran metamorphism and orogeny. So the Conza deposition cannot be post-Usagaran. It's affected by the Usagaran metamorphism. So we can skip the first interpretation. It's no longer valid. The mistake was made that the Conza series is not in time equivalent to the Canberra volcanics, but it is a time equivalent to the lower Isimani series. The field relationship of the described series is nicely seen here in this landscape photo. It's a view towards the southwest. So we see on the right side the craton, which is overlain here by quartzite and quartzite. And here on the left side, we see a pronounced hill, which is made of eclogite, the famous Yalumba hill. And these eclogites are surrounded by accretionary wedge sediments, the lower Isimani metapelites. I've tried to project the profile of this series into the picture. And then we see here the passive margin sequence. Here are the eclogites that are embedded in the lower Isimani series. Here, two pictures of further impression for the field outcrop situation. This is a Great Ruaha. It's a Gengere gorge, where the Great Ruaha River enters the Usagaran belt coming from the Tanzania craton. This is a basis quartzite of the Conza series. Here on the right, we see the poor outcrop situation for the low pressure, high temperature belt, where we collected samples mainly in dry rivers from large blocks. Now I'm coming to the chemistry and the metamorphism of the Palaeoproterozoic eclogites and the associated metasediments. I start with the eclogites, which are part of the lower Isimani group. We found 3 different types of eclogites. Eclogites with morph chemistry, these are the most common type. Orthopyroxene eclogites that are boninitic in composition, and also kyanite eclogites. And all the types are strongly retrogressed. We see here that a hand specimen of morph eclogite, where we have plagioclase and amphibole-rich layers that have been produced by amphibolite phases reworking. Chemically, these morph eclogites plot into the basalt field in the TAS diagram, and the minerals in these rocks are pretty iron-rich and also calcium-rich, the garnet. The magnesium-rich orthopyroxene eclogite plot into the picrit basalt field, and the magnesium-rich and the kyanite eclogite shown here contains kyanite only in layers that are always surrounded by symplectites consisting of sapphirine and spinel. Omphosite is decomposed to plagioclase and diopside, and garnet is always surrounded here by orthopyroxene and plagioclase coronas. The rare earth trace element pattern of the eclogites, the morph chemistry, there are 2 groups, one with very flat pattern, N-morph similarities, and the other one with enriched light rare earth elements corresponding to E-morph. In the morph normalized diagrams, we see a very flat pattern for the N-morphs and a more sloping diagram for the E-morph. The third group have a boninitic composition, which are characterized by a niobium tantalum stuff and an enrichment of thorium and barium, and the characteristic depletion in the middle rare earth elements. So we have 3 types of eclogites: N-morph that derive from the depleted mantle, E-morphs from an enriched mantle, and the boninites from an hydrited mantle, as shown in this zirconium niobium thorium diagram. The retrogression of the eclogites is also seen in a thin section, where we here show here on the right side that the eclogitic minerals, garnet and omphosite, are embedded in a fine-grained, recrystallized, horn-blended plagioclase matrix that forms under amphibolite phases conditions. These are the layers seen here in this diagram. And the omphosite itself is also decomposed in many cases because it has numerous exsolution lamellae of plagioclase in crystallographic orientation. And the garnet has also exsolutions of rutile needles, both for evidence that these minerals have seen higher metamorphic conditions. Temperatures and pressures have been higher. The garnets in eclogites, as well as in the embedding surrounding lower Isimani metapelites, have one thing in common, and this is that the garnets have preserved a growth zone. And this points to the fact that the metamorphism of the eclogites and of the lower Isomani series were a short event, and also the high temperature uplift were short events. It is possible to model the burial history of these eclogites with these preserved growth zoning and with the textures that we find inside of those garnet. For example, we see here titanite rim around rutile inclusion. So this reaction line must have been crossed during burial. And the composition of the strong zoning here and this part of the garnet gives us pressures in the range from 15 to 18 kilobar in a temperature range of 600 to 700 degrees. The peak composition we can't deduce from these zoning because due to corona formation, the peak composition of the garnet and the rim is not preserved. But we can use this rim composition to model the exhumation history of the eclogite. And this indicates that the temperatures at pressures of 8 to 10 kilobars are still pretty high, between 700 and 800 degrees. So it was a very hot exhumation of the eclogite. The peak metamorphic conditions, to deduce the peak metamorphic conditions, we have chosen not garnets which have a preserved growth zoning, but magnesium-rich garnets which were equilibrated or homogenized during the peak metamorphic conditions. They have a plateau in the center of the garnet. And with these compositions in combination with the crossular content, XMG content, also magnesium content of orthopyroxene and the aluminum content in orthopyroxene, we obtain peak pressures and temperatures in this range. And all these isoplates are crossing. This is about 18 kilobar at 850 degrees Celsius. Also, the uplift, again, can be modeled by using rim compositions of these rocks. And these indicate that the corona, plagioclase corona bearing coronas were formed under granulite facies conditions at about 800 degrees and 6 to 8 kilobar. The high temperature uplift that has been modeled by with these eclogites is supported by many reaction textures in the eclogites. So we have always sapphirine and spinel surrounding kyanite. And in the boninitic eclogites, we have very magnesium-rich garnet that is breaking down to sapphirine and orthopyroxene, which has up to 5.6 alumina. Further evidence is granulite facies assemblages around garnet, orthopyroxene plagioclase, as all granulite indicating granulite facies conditions during uplift. Further evidence for high temperature uplift we can obtain from mylonites. Mylonites developed in certain horizons and affected also some boninitic eclogites. And these have protomyelinitic textures. We see here there's a banded rock, and it consists of layers that are dominated by orthopyroxene. Other layers are dominated by clinopyroxene. The orthopyroxene layer shows here orthopyroxene porphyroclasts surrounded by a fine-grained recrystallized matrix indicating very high recrystallization temperatures. And we observe also recrystallization in the clinopyroxene dominated layer, which contains some porphyroclasts of omphacite dissolved. But if you look at the matrix of the mylonite, then we see that plagioclase and pyroxene forming separated grains. And this indicates to me that Omphacite was already broken down to plagioclase and pyroxene. So the melanolitic crystallization occurred under very high temperatures, but already at some lower pressures as omphacite has been broken down during deformation. Similar information we obtain also from felsic mylonites, which are intercalated with the eclogites. The temperature show a high temperature recrystallization as the recrystallized subgrains of this porphyroclast shows lamellae of the exsolution. This indicates that the recrystallization occurred prior to exsolution, and this is prior to the cooling of the rocks, and therefore the exsolution should have taken place at higher temperatures in the critical line of the alkali feldspar solvers. In summary, high temperature recrystallization of pyroxene and feldspars are in accordance with the thermodynamic modeling of the high temperature exhumation history of the eclogites. Now I'm coming to the PT path of the lower Isimani series, which are embedding the eclogites. Also here, we can make use of the reserved growth zoning and can model the burial history of the garnet and growth history of the garnet, which is nearly unzoned in crossular, but strongly zoned in XFE. The peak conditions that we can extract from near rim compositions are at about 13 kilobars at 770 degrees Celsius, which is less than the eclogites in temperature as well as in pressure. The exhumation history, we have, again, for the exhumation, we have textual evidence because all the metapelites contain kyanite, but this kyanite is replaced partly by sillimanite. So this indicates here also a pretty high temperatures exhumation history of the lower Isimani series metapelites. The age of the metamorphism of the eclogites has already determined more than 20 years ago by Müller et al. And we obtained an age by monazite, by sphene, and rutile, and they all indicated that the main metamorphism was at 2 billion years. The lower intercept is mainly determined by a rutile and reflects that the eclogites experienced some reworking of during the Kuunga orogeny. The question is whether in the whole belt the ages are homogeneous or not. The answer will be yes, it is homogeneous. All ages that have been obtained in this area are scattering around 2 billion years. And it has been determined with TIMS, with shrimp dating of an eclogite, lutetium hafnium dating of garnet, and also a monazite dating with a microprobe, all indicate ages very close to 2 billion years. I'm coming to the last unit, reconstructing the PT bath for these granulites. The low pressure granulites with garnet, cordierite, sillimanite occur obviously in a smaller area than the lower Isimani group. The northeastern part of the upper Isimani group, there is not observed whether there is a low pressure metamorphism with garnet cordierite. There is no detailed work done in this area. These granulites have a very unusual texture because they are protomylonites. We see here recrystallized, partly recrystallized feldspars, which are mantled by smaller grains of plagioclase. We see ribbon quartz. So it's a protomylonite. The question is, when did this, what is the timing for this myelonicization? Is it at peak? Is it Palaeoproterozoic? Is it during retrogression? Or is it an effect of the overprint in Neoproterozoic time? Information about the temperatures of deformation can be obtained again from feldspar recrystallization. We see here the same detail in both pictures, that the plagioclase contains absorbed K-feldspar as an antiperthite. And if you look in the recrystallized part of this feldspar, then we see that K-feldspar and plagioclase form separated grains. This means that the recrystallization, the deformation, occurred after execution at lower temperatures during cooling. However, it was still in the sillimanite stability field, as corderite is also recrystallizing. It's the same event, and then replaced by sillimanite-bearing assemblages, indicating that the recrystallization occurred still in the sillimanite stability field. The temperatures must be higher than 500 or even 600 degrees Celsius. The whole series, the upper Isimani group, was affected by a hydration event. We see that garnet is replaced by hydrous minerals or carbonates, scapolite, and also the mafic granulites to pyroxene are replaced by minerals with OH water. And the timing is seen here on the left side in this picture, where we have a recrystallized big antiperthite with K-feldspar and plagioclase, and a replacement from the side that the plagioclase is reacted to form clinosuicide and muscovite. So the deformation on the cooling path was followed by a hydration event. The metamorphic conditions for the garnet corderite gneisses can be deduced from the mineral compositions of garnet and corderite, which are unzoned, indicating very high temperatures or heating for a long time. And the modeling shown here gives results in the range of 820 degrees at 7.2 kilobars. That is in the lower crust, high temperatures. The PT path, the zonation is not present, so we have to rely on textual evidence for the PT path. And we recognize that garnet has grown in a sillimanite stability field. In the decomposition and the retrograde path, the decomposition of corderite and garnet occurred partly in the sillimanite stability field and in the kyanite stability field, because pseudomorphs after corderite or after garnet, they have kyanite and sillimanite in coexistence. So obviously, the PT path passed the sillimanite kyanite stability field during the hydration event. Combining thermodynamic modeling with the textual evidence, we obtain here an anti-clockwise PT path with a late stage hydration event. We have dated the metamorphism of these corderite granulites and obtained by monocyte, microprobe dating of monocyte, and obtained an age of 2.55 gigayears, which is about, in comparison with a high pressure belt, the lower Isimani series, the corderite gneisses are 50 million years older than the high pressure metamorphism. I have combined all the PT paths that I have deduced in the foregoing part in this PT diagram. And I think these PT paths are all interrelated. And after the emplacement of the Upper Isimani series, which shows these anti-clockwise PT paths, the maps pooled together. And this common pooling history is when when the Upper Isimani series was emplaced on the lower. Subsequent to the NAP emplacement, there was this hydration event, and this might be related that the underlying lower Isimani series was dewatering, devolatilization. The data presented allow to deduce a geodynamic model for the development of the paired metamorphic belts in the Usagaran orogen. First, we have to realize that the Usagaran is much bigger than originally thought. It forms a very wide wedge between the Tanzania craton and the Mozambique belt metacraton in the east. The orogenic system consists of a passive margin sequence, which was deposited on the Tanzania craton, and it consists of a oceanic floor. The eclogites were metamorphosed during the subduction. It contains foreland basin sediments of the lower Isimani series, which formed an accretionary wedge. And finally, it consists of the upper Isimani series that were metamorphosed in a very high temperature conditions. And I assume, or we assume, that these sediments have been added to the arc by subduction accretion, and then experienced at a high temperature metamorphism of an age of 2.05 gigayears. 50 million years later, during the Usagaran orogeny, when Mozambique belt metacraton, Tanzania craton collided, the upper Isimani series was thrust over the lower Isimani series and becomes a group. So I think this is evidence that the lower and upper Isimani series present paired metamorphic belts in the sense of Miyashiro that are timely and spatially associated. Evidence in Palaeoproterozoic orogens indicates that we had already here one-sided oceanic subduction in the Palaeoproterozoic. I mentioned that the Ubendian belt also contained Palaeoproterozoic eclogites of morph chemistry. And we have collected the same kind of data set for these paired metamorphic belts, which I will not present in detail, but in short. In this belt, we have at the northwestern end, we have a block, a Bende block, which contains morph type eclogites, and we have the Katuma block, which contains high temperature granulites. From this, we deduced that these are forming a paired metamorphic belt. This has been published by Volker Schenk some years ago. And we assume that there was an ocean between the Bangeulu and the Tanzania craton that was subducted below the Tanzania craton. We have similar data, granulites, PT conditions determined from the eclogites, PT conditions petrologically determined. We have chemical data indicating that there are morph type, N-morph and E-morph eclogites. We have age data indicating that the eclogites and the granulites are roughly of the same age. So we think also these represent paired metamorphic belts, which are slightly younger, 100 to 130 million years younger than the eclogites in the Usagaran belt. And there is a third orogenic belt of the Congo Craton, in the Eburnean Trans-Amazonian orogen in southern Cameroon. The so-called Lyon complex contains eclogites with a similar PT history, and that these are associated with isobarically cooling granulites. So what is the significance of the paired metamorphic belts that we found in the Palaeoproterozoic? If I come back to this diagram of Brown and Johnson, the hypothesis that cold subduction started only in the Neoproterozoic is in contrast to the observation, as we have just described, paired metamorphic belts in Palaeoproterozoic time. They just fall not into the cold subduction regime for, as defined by Brown and Johnson, it should be smaller than 11 degrees per kilometer. But I would not conclude that there was no cold subduction in Palaeoproterozoic time. Rather, I would propose to shift the boundary between cold and intermediate regimes, thermal regimes, to about 14 degrees Celsius per kilometer. And then we find that the eclogites are subductible. And also here in this diagram, the PT diagram, we can see that now more points fall into the subduction regime for rocks that are older than 800 million years. And this shift to about 14 degrees per kilometer is in good agreement with a proposal by Holder and co-authors, who also shifted this boundary for cold subduction on statistical reasons for this data to this roughly to this value. And our data here from our Usagaran belt shows that the subducted eclogite fall into the low TP area and the high temperature belt into the high TP field. So I'm coming to the take-home message. We have seen in the Archean, there are already some subduction-related eclogites, well known from Paleoproterozoic age, also in the Neoproterozoic age, but much more eclogites that are formed in thickened orogenic crust. And the exposed Paleoproterozoic eclogites of mob chemistry and the paired metamorphic belts that I was describing are direct evidence for early subduction processes of oceanic lithosphere, and also that an exhumation mechanism existed that exposed them at the surface. So this is the last slide. I discuss the common characteristics of the known Paleoproterozoic subduction zones. They obviously have shown a higher apparent geothermal gradient during burial. We never found blue schist formation. We have a higher geothermal gradient also during the peak of 12 to 14 degrees Celsius per kilometer. So the subduction was warmer than in Phanerozoic time. The near peak isothermal uplift through the granulite facies conditions may indicate that they were uplifted very fast. And the maximum subduction depths we observed, 60 to 70 kilometers, prior to the isothermal uplift, may have been caused by a slab break-off. Subduction of oceanic lithosphere produced associated high temperature belts, produced paired metamorphic belts, and these were very similar to those we observed in Phanerozoic paired belts. One-sided oceanic subduction started at least in the Paleoproterozoic and at least locally around the Congo Craton in 4 orogenic belts around the Congo Craton. So I hope I have convinced you that paired metamorphic belts and one-sided oceanic subduction existed already in the Palaeoproterozoic. Thank you very much.
Thank you, Volker. Really good. We're going to start moving to question and answer session. So if anybody would like to ask a question, you can either type it into the chat or you can raise your hand. If you would like to raise your hand, and that button for that is along the bottom of your screen in your Zoom window. You find reactions, click reactions, and another pop-up box comes up, and at the bottom of that is the raise hand button. So that's what you would click to raise your hand. If you would like to type it, I can go ahead and ask it for you. So we'll give everybody a moment to get their thoughts together.
So I can't see. Should I skip the sharing the screen?
You can keep it up in case anybody wants to reference a specific slide. It would help. Yeah.
So maybe I start. I have two questions, but one specific I will ask later, maybe when people start to leave. But the first one about difference 50 million years between high temperature and high pressure and low pressure belts. Is it typical? Do we observe it in more recent belts? And how do you explain it that basically high pressure belt record the last event? Is it explanation for time difference?
Yeah, one interpretation would be that we had a very flat subduction. It took quite a long time of subduction. So the metamorphism in the first crust was subducting started already 50 million years earlier, before the collision occurred, and then when the eclogites were uplifted. So it's an early stage of subduction that during which the opposite, the arc was the sediments were metamorphosed in the arc. A flat, long duration of subduction.
And was it observed in other in younger belts? Is it typical?
There are examples, I think, I thought in California, where we have at least 30 million years difference. But you should know it better.
I'm Daniel Wiemer speaking.
Sure, go ahead.
I indeed, I'm a co-author with Volker's talk and study. Indeed, I would confirm this. And in fact, just thinking logically, you have your subduction ongoing for quite some time, while the arc obviously already is forming. So the ultimate deep high pressure subduction, I would assume easily could be shifted in time. If this really is 50 million years, okay, but it is possible, and there are examples. I can confirm this from older parts of the Andes, for example, and those Volker mentioned. Thank you.
Thank you.
All right, Jean Bedard has his hand up, so please unmute yourself.
Yeah, I'll take down my hand. A really interesting talk. I'm glad to have learned something about the Usagaran. But I have a couple of finicky questions and then a suggestion. The finicky one is, you say that your eclogites are morb, but they don't actually look like morb, do they? The heavy rare earths are depleted. There's a bit of a slope. So they're not really morb-like sensu stricto. So why can't they just be an uncontaminated continental flood basalt sandwiched among the sediments that got reaccreted? Why does it have to be more? So that's question one. The second one is, what is the argument that the sediments of the upper group, the low pressure group, are actually arc related? And related to what? I mean, I presume there's a robust Andean margin in the Tanzanian craton that was long-lived. Do the tridal zircons match? Do the isotopes match? I mean, what is the argument that that sediment is not just a lot of continent detritus that got telescoped from the other passive margin, like the Gandir terrain in the Appalachians? So I guess my argument is, why can't this just be failed opening of a basin, and then it got rammed together during the continental collision? You buried some of the stuff to high pressure and squirted it out. It seems your explanation is unnecessarily convoluted. Sorry about that.
Yeah. Well, we don't have any information about the zircon content in the upper Usagaran group. The argument for the arc is just the high temperatures. We have really contrasting metamorphic styles in 2 units very nearby.
Okay, so you can't exclude the possibility these are just a lot of continent-derived detritus and have no relationship to an arc.
Yeah, but why has it been metamorphosed at these high temperatures?
Magmatism?
Magmatism in an arc?
Well, you've got basalts, right? You've got these basalts, the eclogites. They're equivalent terrains in the superior, where there's a lot of basalts coming through, and you cook stuff up and you have very high temperature pressure context.
But eclogite facies?
Well, remember, it's all structurally assembled afterwards. So I worry about these things.
Yeah, okay.
Exactly. Sorry, I may introduce again. Exactly. I think that what Volker is showing essentially is in fact a full association of lithological association for the first time here that would come most closest to what we understand of an accretionary to collisional margin. So obviously,
well, I don't disagree. You've got different pressure temperature regimes that have been structurally assembled, but was it a long-lived arc, or are you just squeezing stuff between colliding continents? I haven't seen the evidence that there actually was an arc, or that those were actually morbed. I mean, well, that's an argument. That's not an observation.
Yeah, I truly agree that, for example, as you said, detrital zircon data would need to confirm this in a sense that, in fact, these sediments, but as I see it, it is the best so far documented example where we have such an association of the eclogites with metapelitic surrounding a larger scale, marginal association.
How does the bonanite fit into the picture, in this picture?
Well, again, are they really bonanites, or are they those fake Archean bonanitic things that are depleted a bit, but not quite enough to really be bonanites? Like your pressures are high, but they're not really quite high enough to get into that other regime. And I think moving the goalposts is not allowed.
Okay.
All right, are we ready to move forward to the next question? Okay. All right, thank you, John. David Corrigan has his hand up, so please go ahead.
Yes, hi, Volker. Great talk. It was very, very interesting. You showed a thin section of what I think is margarite, the root healing exsolution in needles in garnet. What do you infer in terms of that reaction and the kind of the pressure temperature conditions under which that formed. I think it's very indicative of very high pressures, huh? Or is it a pressure temperature thing, or the fact that it has a high titanium content in garnet?
Yeah, I can't give you a right answer. I know that there were some experiments by Masonis some years ago that he explained it by the pressure effect. But I know that also people normally just interpreted it as well. Pressure and temperature were higher, and there more titanium in solution in the garnet. I can't tell you.
Yeah, okay. Yeah, because I think they're from the literature, they're formed in under mantle conditions. So they find them in xenoliths from the mantles, for example. I just wanted to know if there was kind of a PT field pressure temperature. Okay, great. Yeah. Thanks.
Okay. Seems like there's nothing else here. Andre, you said you wanted to come back to something. So I guess at this point, we're out of Q&A territory and it'll be more just an open discussion. So go ahead, Andre.
Yeah, let's, I guess, for Volker and Daniel, I'm wondering, you mentioned carbonate and Conce group in whom Bereza formation, if by any chance you have any samples for it, because based on age, it might be deposited during time when seawater has this highly positive carbonate values, and it would be indirect way to constrain age. So I guess my question, if you have any carbonate samples, probably it's not something you have been interested, or if anyone.
There are some carbonates in the Mount Hill. Yeah, I think one lens is exposed, but I don't have the sample.
Okay. Okay. Thanks.
I guess the result of these monazite ages from the Conce are but quite surprisingly fitting ultimately. So if there was some involvement of seawater, I'm not a sedimentarist, a sedimentologist in that sense, but it is quite surprising that the ages that we can show are clearly texturally metamorphic, match the age of the metamorphism that we observe throughout the belt. So I guess that is the first order answer here.
Yeah, we had a paper with Shared Master on carbonates from Irvin-Sorio belt that record sort of this highly positive values and were deposited around 2.1 billion years. So that's why I'm kind of wondering if these carbonates would show the same signature.
Unfortunately, no samples.
Okay.
I think, Volker, we do actually have a trace element analysis of the monazites, but I'm going too far with that probably. If I'm correct, Volker.
Yeah, from the monazites.
Yeah. So maybe we can really determine that these are of metamorphic origin in that sense.
Yeah, I'll see.
All right.
Paper and kind of ask question if the samples would be available. Okay.
Cool. All right. I think that's all for today then. Thank you very much, Volker, and thank you, Daniel, for stepping in here too. It's great to have you both. So take care, everybody, and we'll see you around soon.
Yeah. Bye. Thank you for coming.
Bye.
Bye. Thanks.